Hello everybody, I'm Vivian Chen, coming from National Taiwan University. Today, I'm going to present my work about automatic key-turn extraction from spoken cross lectures using branching entropy and prosodic semantic features. First, I will introduce our work. I define what is key-turn. Key-turn is a term which has higher term frequency and includes core content. There are two types of key-turn. One of them is keyword, such as a single word, and another type is key phrase, which is a word sequence including more than one word. There are some advantages of key-turn extraction. If we have key-turn list, we can use this key-turn to do indexing for all the documents, and we can retrieve more efficiently. We also can know the relationship between key-turns and segments of documents. Let's see our system as an example. This is a system about cross lectures. If the user wants to know some information about Berkeley algorithm, he can query this key-turn into this system. And if we use key-turns to do indexing, the system can return relevant document more efficiently. This is one of the relevant documents. This is the duration of this document, and we can see Berkeley algorithm appeared at this position. The system also shows the transcription of this sentence and the related key-turns. The user can select one of them to see the detail. The system shows that this row includes a lot of all the key-turns in this document. And the user can select one of them to see the detail. The user can know this key-turn first appeared in the previous document. So the user needs to move to the previous document to learn what is acoustic model and continue to learn this document. We call it backward learning. And there are some key-turns, but not in this document. They are related to acoustic model because they co-occur in the same document, so we assume that they are related. With this knowledge, we can construct a key-turn graph like this one. The graph can show the relationship between acoustic model and other related key-turns. Similarly, we also can see language model and its related key-turns and construct this graph. Finally, if we have the whole key-turn graph, the user can know the organization of key-turns and the relationship between key-turns and segments of documents. So our target is to extract key-turns from spoken cross lectures so that we can get the advantage of key-turn extraction. Let me come to the proposed approach part. This is my flowchart. There are a lot of spoken documents here. And after ASR system, we can get the ASR transcription, and we also use speech signal into our work. The first part is phrase identification. We propose branching entropy to do phrase identification. The target is to connect the word sequence into phrase. And the second part is key-turn extraction. We want to extract some features for each candidate turn and use machine learning method to train a classifier and extract our result. Let me see the branching entropy to do phrase identification. This target is to decide the boundary of a phrase. This is an example. Hidden is always followed by the same word in our corpus, and hidden mark is always followed by model. But this pattern, hidden mark model, is followed by many different words, like this one. So we can know this position may be the boundary of this phrase. With this idea, we define branching entropy to decide possible boundary. Here's a definition of right branching entropy. First, I will compute P of xi. And what is P of xi? See this example. X is the pattern representing hidden, and xi is a child of x, representing hidden mark. So we can compute P of xi to be the frequency of xi over the frequency of x, which is the probability of children xi for x. Then we can compute right branching entropy for x, like this equation. We call it HR of x. So we can use HR of x to decide the right boundary. We find the right boundary where the pattern has the higher HR of x. Like this example, x represents hidden mark model because HR of x has a higher value, so we can know the position may be the boundary. Similarly, we also can detect the left boundary of this phrase. We also use these two equations to detect the left boundary. We compute HL of x bar, where x bar is the reverse pattern like model marked hidden. So we also can detect this position may be the boundary. With this idea, we use pair tree to implement. Here's the pair tree. Pair tree is the tree including all the patterns in our corpus. We also can compute P of xi in this pair tree. Like this example, as previously mentioned, x represents hidden mark in the pair tree, and x1 and x2 are the children of x, representing hidden mark model and hidden mark trend. So we just compute P of x1 and P of x2 in this pair tree. Then we can compute HR of x for each node in this tree. Then we can detect the boundary of the phrase. Here comes to the second part. First, I will extract prosodic, lexical, and semantic features for each candidate term. A candidate term is a term. It may be a word or a phrase decided by previous part. The first set of features is prosodic feature. The assumption is that speakers tend to use longer duration to emphasize key terms. So we can extract each candidate term that first appear in the corpus and segment it into a lot of forms. We can compute this duration of form A, but normalized by average duration of form A. Then we can get a lot of normalized duration for each candidate term. But we only use this 4 value to represent this feature. We use maximal, minimal, min, and rank over all the forms in a candidate term. And we think higher pitch may represent significant information. So we can extract the feature and compute this pitch contour. Also use this 4 value to represent pitch. The other assumption is that higher energy may emphasize important information. So we can extract energy for each frame and use this 4 value to represent energy. The second set of features is lexical feature. These lexical features are very well known because these lexical features can indicate the importance of each candidate term, like term frequency, inverse document frequency, TF-IDF, and POS tag. The third part is semantic features. We assume that keyterms tend to focus on limited topics. So we use PLSA to compute the latent topic probability, like this equation. We can compute the probability of each topic given a candidate term. And how to use these probabilities? We can see this example. There are 2 distributions for different terms. The first one has similar probabilities for most topics. So we can think this one may be a function word. So this distribution tells me this term may not be key term. And this one is different. It focuses on limited topic. So we think this distribution tells me some information about key term. We want to use some value to describe this distribution. And we use mean, variance, and standard deviation to describe the probability distribution. Similarly, also can compute latent topic significance, which is within topic to out of topic ratio, like this equation. This one is within topic frequency. N of Ti and Dj is a number of term Ti appearing in the document Dj. So this one is within topic frequency. And this one is out of topic frequency. So we can compute the significance of each topic for a candidate term. We also use these 3 values to describe the distribution, like previous one. Then we also can compute latent topic entropy, like this equation. This value can indicate the difference between these 2 distributions. We can find that this one has a higher value and this one has a lower value. After feature extraction, we can use some machine learning method to train a classifier, and we can extract our result. We use unsupervised and supervised approaches. The first one is K-means exemplar, which is an unsupervised learning approach. First, we transfer a term into a vector in latent topic significance space, as previously mentioned. Like this, in this space, we can run K-means. The vectors can be clustered into 3 groups. And we assume that the term in the same group focus on a single topic, because this space is latent topic significance. So we find the centroid of each cluster to be the key term, like this one. This is because that the candidates in the same groups are related to this centroid, so it may represent this topic. We just use this centroid to be the key term in our work. In addition, we also use two supervised learning, adaptive boosting and neural network. They can automatically adjust the weights of features and produce a classifier to extract our result. Then comes the experiment and evaluation part. The corpus is from National Taiwan University Lecture Corpus. It is Mandarin Chinese embedded by some English words. Here's the example in our corpus. The same means solution is Viterbi algorithm. Sorry. The corpus is all from a single speaker and lasts 45 hours. For ASR system, we can construct two acoustic models for Chinese and English and use some data from target speaker to adapt the bilingual acoustic model. For language model, we can construct two trigrams from out-of-domain corpus and in-domain corpus and interpolate them into our final language model. Let me show the ASR accuracy. We can see the overall accuracy is about 76. In order to evaluate our approach, we need to generate some reference key terms. We ask some students who have taken this course to annotate the key terms. If the case annotator labeled NK key terms, we assume that he gave each of them a score of 1 over NK. Then we can sum up all scores from all annotators and rank this term by the summation. Finally, we extract the top n bar terms from the ranking list. N bar is the average number of NK. In our work, N bar is equal to 154, including 59 key phrases and 95 keywords. So we can do the evaluation. For unsupervised learning, we set the number of key terms to be n bar and use threefold cross-validation for supervised learning. This is first experiment. We want to see feature effectiveness. This is from neural network for keyword extraction using ASR transcription. This result shows that each set of these features alone gives F major from 20% to 42%. And we can see the green one. If we combine prosodic and lexical feature, we can get a better performance. So these two features are additive. If we see the red one, we can find that we add semantic features, we can further improve the performance. So we can say 3 sets of these features are all useful. Let me show you the overall performance from manual transcription. This is the baseline, which is from conventional TF-IDF score. It just uses double removal and POS filtering. You can see the performance is very poor. And this one is unsupervised TF-IDF. We just use branch entropy to do phrase identification and also use TF-IDF score to rank the key terms. And the improvement is very significant. So the conclusion is branch entropy performs well. For unsupervised learning, we can find that K-means exemplar outperforms TF-IDF a little. And there are supervised learning approach. We find that supervised approaches are better than unsupervised approaches. We also can show the results from ASR transcription. We can see the performance of ASR is slightly worse than manual one, but it's also reasonable. The best result is from supervised learning using neural network. We can get a F1 of 67 and 62. Here's the conclusion part. First, we propose a new approach to extract key terms. We use two ideas to improve the performance. First is, we identify phrases by branching entropy and use these three sets of features together. Our current results are very encouraging. And thank you for your attention.